So now we have our first team talk of this meeting, which we're pretty excited about to see what you guys have in store for us. This is from Jeff Atkins, Cameron Clay, Chris Gough, Lisa Haber, Laurie Hickey, Kayla Mathers, Kerstin Niedermaier, all from Virginia Commonwealth University. So folks, take it away. Thank you.
All right, well, thank you. And Caroline, you set us up nicely. I'm going to make this really quick. I'm just introducing the team here. You will hear from a number of early career researchers from the University of Michigan Biological Station, Ameriflux core site. Much of what we work on is focused on understanding the relationship between disturbance and forest carbon cycling. And so what you'll hear is their work and our work, which is trying to understand how natural climate solutions can be informed by sort of what's under the hood in the Ameriflux tower site, what's going on with respect to disturbance, and what makes for stable ecosystems that are resilient to disturbance, and how can that inform management. So I'll hand it over to Lisa to launch the talk.
Hi, thanks, Chris. So I'm one of Chris's PhD students. My name's Lisa, and I will kind of be setting things up here. Chris, are you advancing slides? Okay, great. So as Chris mentioned, a lot of our work is taking place up at the University of Michigan Biological Station, which is shown here with this massive star on the map. So northern lower Michigan, which is mostly just a regrown forest landscape after clear cutting and burning about 100 years ago. So this forest is really regrown, and disturbance regime has shifted in this location over time from these massive stand replacing clear cut and burn disturbances to a much more patchy partial defoliation from things like wind throws or insect and pathogen outbreaks. So a lot of our research centers on the impacts to the carbon cycle from these more moderate severity disturbances that are dominating in terms of disturbance regime here now. And so also, as Chris mentioned, this is an Ameriflux core site. There are two co-located towers up here. We have USUMB and USUMD, which is in a experimental disturbance from 2008. So Chris, I think we're ready for next slide. And so a lot of the work that we're doing right now, and my PhD and another PhD student, several master's students are working on trying to unravel the mechanisms underpinning a pretty surprising degree of resilience in this forest over time in response to disturbance. So this graph here is showing you years from 2008. I mentioned that was the year that a disturbance was initiated where the USUMD tower is located, all the way through this past year. And what we've seen is at this site over time, compared to the control in green, the USUMB tower, there's a large uptick in net ecosystem production over time following disturbance. So that was a surprising finding. And we're working now to try and really figure out what's going on with that. So in the next slide, you'll see how this disturbance played out, and the one that we're currently working on is playing out similarly in this sort of patchy mosaic of disturbance ranging from no defoliation in part of the stand all the way up to almost entirely defoliated, depending on what species are being impacted by the disturbance and where they're located. So again, we've got this sort of moderate severity disturbance that's very patchily located across space, and we're working to understand how that kind of disturbance is affecting the carbon cycle. So this is sort of our central research question: what mechanisms and properties stabilize forest carbon sequestration following disturbance, and perhaps even lead to a surprising degree of resilience in carbon sequestration. And with that, I'll pass it over to Laura.
Thanks, Lisa. Hi, I'm Laura. I'm a master's student in the lab. And one mechanism or forest property that myself and our lab explores is canopy structure, which is defined through mapping vegetation arrangement. The graphic on the left represents a hit grid of vegetation area index measured using light detection and ranging at 2 different sites. So what you can see is that A more complex forest has a greater number of layers, more variously arranged, like the site on the left, while a simpler or less complex forest is more uniform in leaf distribution, like the site on the right. And then if I can pull your attention to the figure on the right, that's representing data from work at our site that has shown across disturbed and undisturbed forests, including our Ameriflex Tower and other experimental sites at UMBS. Greater canopy complexity supports greater NPP magnitude and stability. And our work has explored that and shown that this canopy complexity factor is a really good integrative property of ecosystem information like species diversity and resource use. And with that, I'll pass it on to Jeff.
Thanks, Laura. So Laura showed you that, with increasing canopy complexity that you tend to get greater rates of NPP. But, complexity is something that really does matter. So I'm going to walk you through this graph real quick. So on the y-axis is a measure called canopy rugosity, which is, kind of an integrative measure of canopy complexity. Greater numbers of rugosities tends to be a greater, more complex canopy. So on this figure, little white circles represent kind of reference stands. And so in those reference stands that you can see that as a forest ages, it tends to, continue to gain complexity even after maybe some other kind of state variables have, kind of stabilized. And so that's part of the reason that we see this kind of mechanistic connection to, greater rates of NTP, the complexities, kind of adding to those processes. The subset in this, one of these reference stands, we can see that we have a control plot and a disturbed plot. And so what this tells us from these stands is that disturbance can actually reset this, kind of complexity successional trajectory here. And we see that in the disturbed plots that we actually see a loss of complexity. So it kind of decouples that complexity age relationship through time. So in that little subset, you can see the orange circles showing those disturbed plots are kind of diverging from those control plots, which are continuing to stay roughly along that kind of successional trajectory. And so with that, I'm going to pass it on to Lisa, who's going to go back into some more disturbance.
Thanks, Jeff. So my little chunk of this has been really trying to examine what's happening at the leaf level physiologically as the forest landscape is experiencing disturbance. So I've been working both in the canopy stratum and also in the subcanopy. And this figure is showing you I think an exciting result. This is what I hypothesized would happen as we are seeing a loss of vegetation area due to disturbance. So the yellow arrow at the top is showing you the direction that disturbance is pushing this canopy structural metric of vegetation area index. A decline in vegetation area is leading to this sort of stimulation of photosynthetic rate in understory leaves. So that's the y-axis here is the subcanopy leaf photosynthetic rate. So seeing this sort of mechanism that may be underpinning greater net primary production in the subcanopy as light is able to penetrate to that layer due to disturbance, you're seeing this stimulation of physiology that could be stabilizing carbon sequestration in that canopy layer, or sorry, stratum, in that forest stratum over time. With that, I'll pass it to Max.
All right, so as you might expect from what Lisa just described as subcanopy leaf level physiology is increasing, so is subcanopy NPP. So as that disturbance is unfolding in the canopy, we see stimulation in the subcanopy helping to stabilize NPP following disturbance. So quickly looking at our figure here, we have our highest severity disturbance in orange. And essentially what we see is the contribution of the subcanopy to overall NPP increasing with our disturbance severity. So in the big picture, the subcanopy is helping to stabilize NPP following disturbance. And with that, I'll pass it to you, Kayla.
All right, thanks, Max. So now we're going to shift our focus to below ground carbon cycling while still focusing on responses across different disturbance severities. So we are examining soil respiration, which is the largest CO2 emission from forests globally. And this is across that same disturbance severity gradient represented as percent defoliation. And this is before and after disturbance. And we are seeing a decrease in soil respiration with increasing disturbance severity. And we're seeing this happen immediately following the disturbance. And these trends are remaining relatively stable into year 3 following the disturbance. So if you can go to the next slide. So this decrease in soil respiration in tandem with increasing above ground carbon cycling and increase in leaf level physiology. This suggests that even at 85% defoliation, we see stability in overall carbon cycling in the years immediately following disturbance at our Ameriflux sites. So with that, I will pass it off to Cameron.
Thank you, Kayla. Yeah, and so for my work contributions to this group, I just wanted to go a little bit longer scale, talking about similar patterns that my colleagues have talked about, but over a little bit longer time scale. You can see here on the x-axis, we have stand age going from 0 years up to over 100 years. And then we have these late successional forest stands on the right of a variety of different ecological communities, all represented in northern Michigan. And what this trend shows is that depending on the ecological community, late successional forests can often sequester through the production of woody biomass in NPP, net primary production. They can sequester potentially as much carbon as younger forests, which we typically expect to be the most productive stage. Obviously, integration of other components of overall carbon storage are critical to better understand this process, but this is an indication that potentially older forests can be managed for as a valuable carbon sink, again, with the caveat that it may depend strongly on the ecosystem type. This work also relates to the work that Kayla and others did in that. We have 2 different treatments here, a cut and burn treatment and a cut only treatment. And in terms of change over time, we saw no significant difference in these 2 different treatments at this particular site in terms of NPP production over time. With that, I can go ahead and give it back to Kayla, who's going to help wrap us up.
All right, thanks. So to summarize, better understanding mechanisms of forest carbon cycling stability is a crucial component in the development of natural climate solutions. So to end, we are translating our findings into general forest management goals through the lens of natural climate solutions. So we'll leave you with these 3 take-home points. First, management for structural complexity may enhance carbon sequestration stability and strength. 2, because above and below ground carbon cycling responses may diverge and offset from each other, quantifying both in the face of response to disturbance is important for carbon budgeting and accounting. And then finally, in contrast to previous hypotheses about succession dynamics, we found at our site that the preservation of middle to late successional forests may support carbon sequestration. So thank you so much for listening, and we will take any questions now.
It's great. Thank you so much. I really enjoyed that team talk. So we have a couple of minutes for questions. Again, if you guys want to raise your hands if you've got questions, and anyone from the team take those questions.
So may I ask one question? Yeah, thank you for a good talk. Your complexity, canopy complexity is measured by VAI. So that most based on geometry, structure of canopy. My question is about how about the diversity? So the diversity contribution to the recovery, resilience of the tower site. Do you have any data and results about that? Okay.
I'd love for an early investigator to jump in, but I'll just say that we do have data that suggests in higher diversity systems, diversity is rather important to resilience and recovery of NPP. UMBS has a very low tree richness, and so diversity seems to be secondary to structural complexity. I think that's probably different if we moved, say, to the tropics. I don't know. Somebody, Jeff, you might add to that.
Yeah, I want to jump in. It's what Chris is saying, is that diversity or biodiversity in this case, particularly tree diversity, is sufficient but not necessary. In fact, within the Great Lakes region, some of the most diverse stands we have found have been predominantly just sugar maple. But like Chris said, there's definitely a latitudinal gradient in that, and that plays a part of it as well.
Great, thank you. I'm sorry, but in the interest of time, we'll need to move on to our next speaker. Thank you so much again for that fantastic team talk.